We are going to look at rearranging fruits. We have two baskets in this question, basket 1 and basket 2, represented by zero indexed integer arrays. And the cost of the fruits in basket are represented by elements. So the objective is to have both the baskets equal after they are sorted. And what we can do is we can swap out elements. So the objective is to get minimum cost. So the cost is the minimum value between the two elements we choose to swap between B1 and B2. That's our cost. And what we have to do is get the minimum total cost, which is the sum of all the swaps. So this is the question, and we also know that the constraint on the length of basket 1 and basket 2 is 10 power 5, and the size of both the baskets are going to be the same. That's a key insight. And when we see 10 power 5, it kind of gives us a clue that the maximum complexity should be uh, n log n. This is just a clue whenever you see 10 power 5. So you can think that the time complexity should be O of n or O of n log n. Okay, so this is the input and output. We need to return an integer, which is the sum of minimum cost. Now, for insights, how do we approach this problem? So, we immediately think of making the frequency of each element equal across both the arrays, because we don't have to worry about the order. Once it's sorted, it has to be equal. So what we need to do is match the frequency of each element. Match frequencies. And if the frequency across board is not even, that means that it can never be um, made into two equal baskets. So for example, I had an element 5. No matter what swap I do, there will always be one 5 which is standing out, and I can never make both the baskets equal. Or if I had three fives, it's the same case. I can put one 5 here, but again, another 5 would always be left as odd. So we can say that the frequencies have to be even. Okay. And the third is when we look at the frequency, when you have, in this case, you have 4, you have once, and the element 2, you have thrice, and here you have 1 twice, and you have 2 once, and you have 4 once. So if you look at 4, you can say that this has 1 4, this has 1 4, then you're all set with 4. You don't have to do anything. When you look at 2, this has 3 twos and this has only 1 2. So the difference between the frequencies is 2. So the difference in frequency of 2 is 2. So what you should do is take away half of this and give it here. So the frequency difference, the difference in frequency by 2 is the number that you want to swap, like that's the number of elements you want to swap of that kind. So I hope that's clear. So calculate the difference in frequency. Another key insight that I first failed to notice is we have to minimize the cost of each swap, and we do not want to minimize the number of operations. So we can have more operations. For example, let's take this basket 100, and the second basket, and the second basket 150. So if the goal was to minimize the number of operations, then I could have just said swap this and this. You do one swap and then you will have 150 150, and it makes both of them equal. But what would be the cost of the swap? It would be 50 is the minimum between the two elements. Instead, you have 100 150. Instead, if you decide to swap with 1, you decide to swap 1 and 50. I know 1 is equal in both the places, but you choose to swap with 1 because that will yield you very little cost. This swap would cost you only 1. So this would result in 50, 100, and 150. So now what you could do is you could swap 1 back to this one and get 100 from here. So that would again cost you 1. So this would be swapping these two, 50, 100, and 100, 150. So the total cost became 2, and it's not going to be as high as 50. So we can choose to swap with the smallest element, and if that yields us better results, we can do that instead. So I know the number of operations is double, like you have to do that twice as opposed to once, but we only care about the total cost, as in, yeah, the minimum between the two elements. I hope this piece is clear too. Okay, so another key insight before we proceed with the solution is, um, the number of elements to swap from both the baskets would be same. So if not, we cannot achieve uh, equality. So the number of swaps are equal. So let's take one example, 1 2 2 and 1 3 3. So there is a match. We have even frequencies of 2 across board, so we can work with 2. And there's an even frequency of 3 across board, so we can work with 3. And now we eventually swap these two. This is case 1 where you have all elements. Sorry, we have the. So this is first case where all occurrences of that element appears in one, and this would mean that all occurrences of another element appears in the second one automatically. If not, we'll have uneven frequency that would lead to a -1. So the other case is straightforward, where we have 150. Other case is straightforward. It's like the main example that we saw. So the other case is straightforward. It's like the other example that we saw. We have the element appear in both the baskets, but the frequency doesn't match. Like you have more of 50 here and more of 1 here. So if you do a swap between 1 and 50, you should be all set. So either way, the number of elements that you swap from basket 1 should be equal to basket 2. This means that when you are building your, so you want to calculate, so you want to calculate the difference in frequency, and as you calculate you will be building your merge array, building a merge array which you will need to swap. As you calculate the differences, you will be building swap array. So this will get all the elements from both the arrays that needs to be swapped. So it doesn't matter from which array it is, because you need to do the equal number of swaps. So you can just worry about the first half of this after you sort. So you can look at only these, because it will eventually be swapped with the other basket. I hope it's clear. Board, we have two baskets. Uh, so we have two counters for each basket, and the space complexity is O of n. We'll look at that later. And the swap is the total elements that requires swapping, and the minimum element is initially set to infinity. So we iterate through all the keys, the combined keys from B1 and B2, and um, we find the total number of times the element has appeared. If the total number of times the element has appeared, that is the frequency, is odd number of times, we can short circuit and return -1. If not, we proceed and we try to get the minimum element by comparing it with our current minimum element and key. And the difference between the frequency in basket 1 and basket 2 of the key, of the current k, um, is the absolute difference between both of them, and the number of items that we need to move across would be difference by 2. So difference by 2 is the number of times we will add our current key to our swap array. Once we have the whole swap array, we don't need to process the whole thing. So we can sort it and process only the first half of it. And we have a choice to make. We can either choose the smallest element. Since it's already sorted, this would be the smaller one of the two. We can choose between the current element and the minimum element swapped twice. So we can choose between these two, and after adding up everything, we get the result and we return the result.